Good afternoon, everyone. Thank you for coming back to the afternoon session of the H-Space. I would like to introduce myself. I'm István Arnócz, the Secretary General of the Hungarian Astronautical Society. So this is the, let's say, second organizer of this event. What I would like to just introduce you to is that this event is one of the many events that the Astronautical Society of Hungary organizes. It's very important that we, as an Astronautical Society, we are here to give a platform to people who are interested in space or who are working in space. This means that we are organizing events for the Hungarian society, for the 10 million Hungarians in Hungary, but we are also organizing events for the space researchers and space entrepreneurs. So if you find interesting this event, I think you will also find interesting all the events of the Hungarian Astronautical Society. You can visit mont.hu/események, where all our events are there. And if you want to get more information, you can be a member of the Hungarian Astronautical Society, where you can get extra information and you can get much closer to actual space researchers, get invited to researches, satellites, etc. And I would like to introduce the chair of the session, Dr. Földváry Lóránt, who is an associate professor at the Department of Geodesy and Surveying, and also the Hungarian ESA delegate for PB-NAV. Lóránt.
Yeah, thank you very much. It is my pleasure to welcome all of you in the first scientific session of the present H-Space conference. This session is titled as Science and Technology. Since this label, since this title is covering quite a wide range of disciplines, in the same way I assume that the 8 talks considered in these sections will be also quite diverse. Therefore, we will have quite interesting and hopefully triggering presentations. Let me wish you quite fun and many interesting talks for the audience. And let's start the presentation. Our first presenter will be Péter Vári from the National Media and Info Communication Authority, and the title of his presentation is "The Future of Satellite Frequency Usage Satellite Agenda Items for WRC-23 and WRC-27. Let me give you the floor.
Good afternoon. My name is Péter Vári, and I'm the Deputy General Director at the National Media and Information Authority. And I tell you too, I'm not the astronomer, not a meteorological expert, but I can see this field in a different way, because we can see clearly what frequency required for these fields for the future. How we can see this area, these sectors. The ITU organized the radio conference every 4 years, and that time the experts, the experts sit together and try to decide which frequency use for the future, the different purposes, the terrestrial, the satellite, and communication, space research, for example. And the ITU is the international organization, 193 members, countries, and they have the sectors. One of them, the ITU telecommunication. Thank you. the standardization sector, and ITU-D, the development sector, and ITU-R, the education sector. This last one will be interesting for us. The ITU radio conference, as I mentioned, hold every 4 years, and this is a long. It seems to be a long period, 4 years, but necessarily discussed a lot of details how we can use the spectrum for different purposes. We can see the WRC circle. We are beyond the WRC-23. It was the end of last year, and that time a lot of the spectrum experts decided about the future, how we can continue. And end of the last week, decided about the future, what will be the topic, the next WRC, the WRC-27, for example, what necessary to discuss, what necessary to the measure in the different field, how we can accept it, the worldwide or as part of the world, the different spectrum, for example, the radio astronomy or the space communication. This is 4 years, as I mentioned, and it's separated into more parts. One of them is CPM1, and it is a conference preparatory meeting. That time, it's the first time when we try to discuss what is the result of different topics, and we continue the work together. The international region, because as I mentioned, maybe that our world is separated into 3 parts: ITU 1, 2, and 3. The Europe and African belongs to the region 1, and the region 2 is the American continent, and the region 3 is generally the Asia Pacific area and the Asia. Let's see what was the topic in the last WRC. It was the last December. We can see that we had a lot of interesting items what we discussed together. What the future. I only mentioned some example what is interesting for us or the researchers for the future. For example, let's see the 45 megahertz band. This is the second allocation to the Earth exploration satellite. It's active service for the space active satellite to detect the ice and the water. The background is the mapping of the subsurface layers, ice sheets, aquifer layers using the sensor in the space. We can see some example where we can see this area generally. And the second allocation, ES active in the 40 and the 50 megahertz band also. This is a new solution, a new opportunity to discover our world, discover the ice and the water in our world. Let's see the other agenda item, 1.13. To consider possible upgrade of the allocation of the frequency band 14.82, 15 to 35 gigahertz to the Space Research Service in accordance with the resolution 661. The background of this that the data relay system are used in the uplink and intersatellite direction, the high capacity data transmission from the GSO orbit or between the non-GSO and GSO the satellites. The allocation for all direction is upgraded in the 14.8 to 15.35 gigahertz band, maximum to 2 billion kilometers from Earth. The condition to protect the existing services accepted the max PFD value, and it was depends which services used in this situation. For example, the Max PFD, it's a radio astronomy, and other Max PFD belongs to the, for example, the space to Earth links. And let's see the other interesting question, what we discussed. To review and consider the possible adjustment of the existing or possible new primary frequency allocation to ESS passive in the frequency range 231.5 to 252 gigahertz band. It seems to be very high frequency to ensure alignment with the more up-to-date remote sensing observation requirements in accordance with the resolution 662. The background of this item that the measurement of the ice clouds and the atmospheric molecules and gases, the nitric acid, the ozone, the sulfur dioxide, oxygen, the nitrogen oxide. It's a new allocation for the ESS passive in the bands the 239.2 to 242.2 and the 244.2 to 247.2 gigahertz. We can see the picture about this spectrum, why interesting for the space research, this frequency, and let's see how can use this band and what kind of sensor will we detect this different the gas. The agenda item 1.15 and 1.16 is the harmonized to use the frequency band the 12.75 to 13.25 gigahertz. It's Earth to space by GSO FSS Earth station in motion. It's called eSIM. The agenda item 1.16 to study the developed technical, operational and regulatory measures to facilitate the use of the frequency bands the 17.7 to 18.6 gigahertz and 18.8 to 19.3 gigahertz and 19.7 to 20.2 gigahertz. It's a space to Earth, and the 27.5 to 29.1 gigahertz and the 29.5 to 30 gigahertz. This is Earth to space the direction. The key band by non-GSO FSS ASIM. The new resolution were adapted for the Q band and the GSO ASIM and for the key band the non-GSO ASIM. In this case, the harmful interference, only the notifying administration is the one of who responsible to eliminate the interference, while the other potential involved administration may collaborate on the voluntary basis. It will be very interesting how we can handle the harmful interference questions and how we can send the report to the administration that we measured or we realized there's some problem or harmful interference in this spectrum and in this services. Let's see the 1.17. It's also very interesting when to determine and carry out on the basis of the ITUR studies in accordance with resolution 773, the appropriate regulatory actions for the provision of the inter-satellite links in a specific frequency bands or portion thereof by additional addings in the inter-satellite service allocation were appropriate. We can see that some frequencies also, it was interesting that how can accepted the use these bands when we when we established the GSO, non-GSO network. Okay. And agenda item 1.18 and the 19, and agenda item 7. It was interesting that the new allocation to the mobile satellite service for the narrowband system, it was the result of nothing of change. It's nothing happened, and let's see other frequencies, what will happen in the future. I mentioned that in the last week accepted the new items, the new topics, the next WRC, what necessary to discuss together. And we can see that some frequency, some bands which will be interesting, for example, the Q and V band, FSS arrow, and the vessel, the AirSIMs, for example, or we can see the limit unauthorized operations of the NGSO, FSS, and MSS Earth Station, for example. And it's also interesting, first, the low data rate, non-GSO MSS in the L band and S band. It was accepted together by the members of the ITU, and 2027 we will discuss this question. This is a overview about the future. Which frequency, which bands will be interesting for the space communication or space research in the next 4 or maybe the next 8 years. Thank you very much.
Thank you very much. We have a time for a short question, if there is any. Don, please.
Okay, thank you for this question. Now I can speak only the spectrum, which seems to interesting the satellite and the space research, for example. But the total picture that the spectrum uses different purposes, not only the satellite communication. Some frequencies which I mentioned used by the terrestrial network nowadays also, and it is really big discussion that how we can continue, because we have some existing service nowadays. Maybe it's used maybe the old technology, and we would like to switch off this technology, and we would like to forget the old technologies, and we would like to open the new way, the new technologies, including the satellite communication, for example. It's very, very difficult to agree at the worldwide level, because the different countries are the different technology level, and different demands from the different countries, as we see. And we participate in the common work, and we have a lot of the working groups, and we try to agree the different technical backgrounds. We try to measure that this solution causes any problem to the civil or non-civil service, for example. And after we discuss inside, for example, our country, discuss the European level, it's called the CPT. And after we go to the ITU1 region, and after we sit together for 5 weeks, and necessary to agree the different parameters at what we can use for the future. In this way, we agreed that what is the next direction, what is the next interesting, the spectrum. Of course, it's come from the industry, that it's interesting because we have the new solution, we would like to use the new bands, for example, but necessary to discuss the worldwide level, especially in the space communication, that how we can launch this new service and how we can avoid, for example, harmful interference, because it will be the worldwide problem in the future if we cannot agree. It's very difficult to this work, but on the other hand, it's very interesting that when we see the new technology, new solution, and the new bands, for example, how we can use the other purposes, for example. Okay, thank you.
Thank you again. Our next presenter is Ákos Kereszturi from Konkoly Observatory, and the title of his presentation is Hungarian Participation in the Comet Interceptor mission. I give you the floor.
Thank you. Thank you. Good afternoon, everybody. Okay, so back one, please. Yeah. That's, okay. So the Comet Interceptor mission, what I would like to talk about, I'm Ákos Kereszturi at the top right, but I'm the one who is talking. But the rest who are listed over there are the persons who are working on this mission, actually I have to say. Okay, with this I can switch the slides. Okay, so what about this Comet Interceptor mission? It's a quite interesting mission, I have to say. I have been involved right at the beginning of the idea to make such a mission. The idea in the background is like this. Ah, good, okay. So, the concept, we need to to visit a comet which comes for the first time close to the sun. It's very good. Nobody has ever visited such a comet. But after the discovery, you have 1 or no more than 2 years to reach this comet. So you need to be a probe out in the space, which is waiting to be discovered, a good comet, and then go to this comet. So this is the idea in the background, because it provides a lot of information on the formation of the solar system, early processes, and so on. So no such mission actually has ever launched without a specific target. So we still do not know what will be the target, but we know when the mission will launch. The target comet will be discovered with LSST, the Large Survey Telescope, based on statistical basis. Actually, it is a trio of probes, so 3 probes. The main probe, the main probe, and 2 CubeSats. Actually, the ESA CubeSat has been deleted because of financial reasons about 2 years ago, and then they realized, several years ago, and then they realized, okay, we have money, so it is back in business. So we will have 3 missions, 3 probes, and after the launch, they will wait at the so-called L2 long-range points. Here is the sun somewhere, here is the Earth's orbit, and here is L2. So the probe will be waiting here till the discovery of a good comet. A good comet which approaches the sun for the very first time. So it comes very fast on a parabolic or hyperbolic orbit. It has been orbiting around the sun for 4.5 billion years, very far away, and come back to the inner solar system. The problem, we do not know what will be the relative speed. That's quite strange. I'm trying to point, good. What will be the relative speed of the proper comet? And what will be the orbit of the proper comet? What will be the size or the brightness or anything else? So nothing is known. This is the difficulty to specifically design the payload, because you do not know what to look for. But we need to give some rough approach. So there is a statistical estimation. There is probably 1 comet like this in a year, based on the current knowledge. It is a so-called F category fast mission, 150 million euro without launch. and it aims to be launched in 2028 together with the Ariel Space Telescope, and it will wait in the L2 point. There are several difficulties. First, the relative flyby speed can be very, very high. And what if we will not find the proper comet? We have a mission there, a probe there, and waiting for many years. Of course, after 5 years, it will reach a, let me say, regular, well-known comet if there is not a new target. But hopefully, it will reach a brand new comet. I mean, regarding the new in aspect that it will come first close to the sun. But there is a lot of unknowns. And here you can see the schema of the flyby. There is the main probe, which will go in this, roughly this line, relatively far away from the cometary nuclei. And there will be two small CubeSat category probes from ESA and from JAXA, and they will reach much closer, approach much closer the comet. It will be a bit more risky, but of course it's more interesting at the same time, and they will broadcast their observations to the main spacecraft, and the main spacecraft will transmit the data toward the Earth. Yes, what can we expect from this visit? You can see the well-known image of Churyumov Gerasimenko, which is not a comet which came for the first time close to the sun after its formation, but it's a periodic comet or a comet that visited several times the sun. But there are still a lot of interesting things on this type of comet. And here is another one object which is visited by New Horizon far after the Pluto flyby. So this is how a very far object on the Kuiper belt looks like. I mean, this is one example, the only one that we have. So what we are waiting for as a discovery from this mission actually are, we will have information on the composition, on the primordial material of the planet formation, presence and characteristic of ices and organics there, what is the shape, what is the density of such an object. Not like this, we do not know what it will look like. But, so it will show something about the coalescence and planet formation and the surface features, very old impact rate, surface evolution beyond the heliopause, where it was orbiting for 4.5 billion years. So it's quite an interesting, and there is still one more possibility. What if it will be an extrasolar object? It will be even more interesting. There is a certain chance, not high, but a certain chance that it will be an interstellar object. So what about, how does it look like? Here you can see a rough image of a plan of the probe, and you can see the main payload, optical camera, mass spectrometer, infrared camera, and dust and magnetic detectors. So let me say the classical items. Regarding the Hungarian contribution, based on our ESA budget, we already have a products-based agreement, and supported by the Ministry of Foreign Affairs and Trade, and two main contributions, or actually three main contributions. One is the COCA, the Comet camera. Here you can see, where two companies, Remred Ltd and SGF Ltd, are providing the software and the hardware, and we, as the Concol Institute, providing some science and some coordination-related activity. And also there is the Admatis Ltd, working on thermal insulation, and the Wigner, working on the plasma and related instrumental aspects. So here is the COCA, the Comet camera, and here the DPU, the digital processing unit, somewhere here, is designed and being made here in Hungary. So these are the main characteristics of the camera. It is the diameter like this, 13 centimeter diameter, very much similar to the Cassis, which is on the TGO orbiter around Mars. Here you can see some parameters of detectors, field of view, filters, exposure time. It's quite high, quite huge, the range. The memory, data storage, and so on. So here in this panel, you can see the DPM, the digital processing module, what has been designed, tested, and will be soon produced in Hungary by these two companies, Rembrandt and SGF. Yes, so some examples what was like the work, or what is it like. Here you can see a rough timeline. The main point is it is a one-time opportunity. So you fly by the comet and do a lot of observations and ends. Everything finishes, not crashes like this, but hopefully finishes, and you need to broadcast back. The problem, you do not know what will be the relative speed, what will be the brightness, and a lot of parameters are not known, and you will have a short time to do everything. So this required a very sophisticated, but at the same time very specific planning. Thank you. So what is the work like? We need to forecast potential parameters. Actually, one BSc diploma thesis was done like this. Consider a range of flyby speeds, range of albedo, range of color properties, and so on, and to do some instrument operation scenario for this, for the not well-known thing. It's quite difficult. So how is it being done? We have a lot of Zoom meetings, weekly progress meeting, monthly progress report, and we are actually here, the EFM and PFM model in the phase CD, so it's quite close to the finish, let me say. And what our scientists can provide at this phase? For example, okay, but what will be the exact parameter of the color filters? There was a lot of discussion. Okay, what kind of overexposure should be accounted for? What can be the smearing related possibilities and range? So we need to define and model a lot of things, and of course compile the red book, which is the basic book of the mission documentation, which is about 130 pages, if I am right, if I remember well. So actually, the progressing is according to schedule. A lot of lessons learned, a lot of technical experience is needed, and some technology transfer actually happened. Western companies do not like to give their technology, but actually when you are discussing problems with the mission, they should provide a lot more, the engineers themselves, than the company should allow officially. But the engineers will tell you a lot about, okay? So I don't want to say much more about the main problems that we encountered are the increased lead time of critical items and the increased cost. Actually, several people say it is because of the so-called post-COVID era. It is a character of the current years. I'm not an expert of this, but actually the lead time increased a lot, and the cost also increased a lot in the last year. So actually, but it is quite useful as a strategic experience. I think the science engineering synergic project is like that, where Hungary has a good possibility and the possible business, but it's not business hall, piacirés, yes, a market gap where we can have some possibility to make similar missions or something like that in the future, but I think it's quite perspectivic and useful. Thank you for your attention.
Thank you very much, and we have time for a question. Yes, Mr.
Based on the orbit, you can estimate if its orbit is very elliptical, very highly elongated, parabolic or hyperbolic, there is a good chance. You cannot be sure, but it is a quite good chance. There is very low probability that a comet which is on a very, very elongated orbit has already came close to the sun, because actually you can think based on Newton's law and like this, if in your mind, the orbits are stable. In the solar system inner part, yes. But if a comet is coming from above 1,000 astronomical unit, there's no such sense that stable orbit. There's orbits for billions of years, and our solar system is traveling across the galaxy. There is the galactic tidal gravity field. There are close-by star transits. So you cannot be sure, but there is a good chance that it will be, based on the orbit, it will be a first coming.
One more question.
Since the Lagrange point is quite unstable, isn't it a bit wasteful to park several space vehicles there? Because they will gravitate around each other.
I do not think it's based on the gravitational effect they will collide each other. So I suppose it's moderately stable if you are considering the time scale of years. You should have, and probably can have enough possibility to control the position and the movement of the spacecraft in a safe way. So if you leave them intact for decades, they will go away, but these are the time scale of years, and you can adjust the orbit in the time scale of years.
Thank you very much again. And our next presenter is Lady Judit Fogasy from Konkoly Observatory. The title of her presentation is Radio Interferometric Observations of the JUICE Spacecraft en route to Jupiter.
Thank you. Welcome everyone. I'm going to talk about the JUICE mission and the Hungarian involvement in the radio interferometric observation of the JUICE spacecraft. They are my colleagues, and we are actually a quite small group working on this project. So first a bit about JUICE. JUICE stands for Jupiter Icy Moons Explorer. And as the name suggests, it's going to study Jupiter's icy moons, but also the complex environment of Jupiter. Why do we care about the Jovian system and about Jupiter in particular? We care about it because Jupiter is kind of an archetype of giant, gas giant planets. And by studying Jupiter and the moon systems around it, we can gain knowledge which can be applied later studying exoplanets. And the JUICE mission will consider two key elements of the ESA's cosmic vision. The first question is what are the conditions for planet formations and emergence of life? And the second question is how does the solar system work? And hopefully JUICE with its instruments and science goal will address these questions. So the three moons JUICE will study are Europa, which is a young active surface, and it may even went water vapor into space via plumes. So hopefully JUICE will study that in depth. It will also study Callisto, which has the oldest surface in the solar system, and it also probably contain salty subsurface oceans beneath the icy crust, and the primary target is Ganymede, which is the only moon in the solar system which generates its own magnetic field. There will be several flybys around these moons, I think 35 in total. As I mentioned, JUICE will also study Jupiter's complex environment, its atmosphere, its magnetosphere, but also the magnetic environment around Jupiter. It will study the volcanic moon Io and also the dusty rings and the other smaller moons of Jupiter. Okay, so JUICE was launched last year in April. And apart from a small problem with deployment of one of the radar antennas, everything went fine. Now that problem is also solved. Everything is according to plan. And it will reach the Jovian system in 2031. 3 years later, the Ganymede orbit insertion will be done, and the mission ends roughly in December 2035. But even before reaching the Jovian system, there are 4 key events during the journey of JUICE, which consists of gravity assist maneuvers. The first one will be this August. It will be a Moon-Earth flyby. And there will be another flyby, a Venus flyby, actually next year, August, September. And there will be 2 other Earth flybys. Okay. So there are 10 onboard instruments on JUICE, and there's also an extra one, which is actually an experiment. It's the planetary radio interferometer and Doppler experiment, and our group is working on this project. So as I mentioned, PRI stands for Planetary Radio Interferometer Doppler Experiments, and it doesn't have an onboard instrument, but it uses the radio communication system of the spacecraft itself. And the main goal of PRIDE is to enhance the science outcome of the whole mission by providing very accurate spacecraft ephemeride, so spacecraft position. And to do that, it uses the VLBI technique, very long baseline interferometry technique, to observe extragalactic radio sources as reference sources. And it also uses the Doppler measurements of the carrier signal to obtain radio velocity measurements of the spacecraft. So the advantage of the VLBI technique is its really high resolution, or the achievable resolution we can get. And the bigger the distance between 2 antennas, the higher the resolution you will get during your observations. And to achieve that, there are several antennas deployed all over the globe, so we can reach really high distances between the antennas, thus reaching really high resolutions, milliarc-seconds resolutions. The PRIDE hub is in the Netherlands at the Jive Institute, and the 2 main components of PRIDE are the radio telescope networks, which is provided by the European VLBI network. And the other thing we need are the celestial sources, so quasars, radio sources in space. The International Celestial Reference Frame, ICRF, contains a couple of thousands of radio sources, quasars, which can be used for reference sources. They have really accurate position measurements and flux density measurements and so on, and they are studied by VLBI observations. The problem with ICRF reference frame is that we don't have enough sources along the trajectory of JUICE. So we need to find additional reference sources, especially in-beam reference sources. In-beam phase referencing means that the distance between the spacecraft and a quasar is less than an arc minute, or maybe just 1 or 2 arc minutes. So we need to densify the reference frame. And within the project we are doing here, this is our main goal, and to do that we use several radio source catalogs, and we try to compile our own catalog for potential reference sources, which can be later observed by VLBI measurements, and hopefully we can use them as phase reference sources later during JUICE operation. Our team participated in several pilot VLBI campaigns, not only for JUICE, but also for Bepi Colombo and Juno. And these projects are all mostly observed. We are waiting for the data to be correlated, and then we can analyze the data and hopefully find many new phase referencing sources. And the one campaign I'd like to talk a bit more is related to the Venus flyby of JUICE, which will be next year at the end of August, beginning of September. Why do we care about this flyby? This is a perfect opportunity to test the pry technique itself and also to check that how well the pry technique can improve planetary ephemerides, in this case the ephemerides of Venus. So it's an important test before JUICE arrives at the Jovian system. And I don't know how well you can see, but there's a line with an arrow, that's the trajectory of JUICE, before, during and after the Venus flyby. And the downwards pointing triangles represents ICRF sources. There aren't many along the trajectory at this time, especially not in-beam reference sources. So we selected from different radio source catalogs 12 potential candidates for phase referencing and observe them using the EVN facility. Again, we are waiting for the data to arrive. It's being correlated right now, so hopefully soon we will get our hands on the data. So this is the main goal of our project. And as a summary, I'd like to leave this infographics of JUICE. Thank you.
Thank you very much, and we are asking for questions. Then let me ask you a question. It is about this in-beam densification of the quasar sources. I mean, in a way, we don't know what will be the actual timing of the arrival of the JUICE to the object. So how can we guess that which area should be surveyed more frequently to identify further quasars, further objects? Maybe the question is not proper. Okay.
It's a valid question.
Okay.
Yeah, I think the ephemerides of June are actually planned. So there were calculations done during mission planning to actually know that at which time where the spacecraft will be. So we kind of know where to expect the flyby. Obviously, the more reference sources we have, the better, just in case, and also to have more options for the phase referencing.
And if I understand correctly, in this case, the densification just means that you also try to identify quasars with much weaker signal, which was not that much in the focus so far. Am I right?
Yeah, that's correct. Yeah, that's correct.
Thank you very much. And our next presenter is Sara Sanchis Climent from KTH Stockholm. And she's going to present us about SPECTRE, a self-deploying bistable composite tape spring mechanism for future nanosatellite missions. I give you the floor.
Thank you. Good evening, everyone. We are going to talk about SPECTRE. SPECTRE is a student experiment, and it's a self-deploying bistable composite tape spring mechanism for future nanosatellite missions. So, in our team, well, specifically we are here, me, Sara Sanchis Climent, I'm the team leader, and Julien, which is the mechanics leader of the team, and we are from Spain and France, but we come from Sweden, from KTH, the Royal Institute of Technology. In our team, we are 12 people at the moment, and it's quite an international team. We have 10 different nationalities. The only one repeated is the Swedish one. And so we have to work together, and I included it because it's the topic of the conference, talking about internationality too. To fly our experiment, we are using Rexus Vexus, which is a program that was realized under the collaboration between the Swedish Space Agency and the German Space Agency, DLR. And there are much more companies involved, like Swedish Space Corporation, Morava, etc., and mainly the European Space Agency. During this program, they allow students to fly in rockets, in sounding rockets, and in balloons, different experiments. Every cycle, which lasts 1.5 years, they launch 2 sounding rockets and 2 balloons, with a total of 20 experiments that students can launch and do test whatever the experiment is about. Apart from that, we launch everything from Kiruna. SSC has a headquarters there, which is the S-Range Space Center. And there we launch our experiments. We are in the Rexus part, so we launch it in a sounding rocket that gets to 80 kilometers of altitude. And during the whole process, we get mentorship from all the companies that are involved, mainly European Space Agency, all the other space agencies, Swedish, German, etc. And they try to follow the way that projects work in the space sector, so we as students can also work as it will be in a shorter period of time. But in this project, yeah, in our cycle, these are all the other teams involved. You can see that there's one, Taylor, which is also from Hungary. They are here. They presented a really nice poster, if you want to check it. But there are teams from many different nationalities. There are a lot of German teams, the Hungarian, us from Stockholm, and there are others from Romania, and also from Sweden, from another part of Sweden. But now let's talk about our experiment. What is SPECTRE? Our experiment wants to validate a composite tape stream boom, which in the end is a mechanism to deploy things in space, but it's made of composites, so it's lighter and has a lower volume. I brought one from the back. I don't know if you can see it, but this is a composite tape stream boom. It's made of a composite material of fiberglass and epoxy ply, and it has a bistable property, so as far as you start deploying it, it deploys on its own. And yeah, in our design, this is the deployment mechanism we are going to use. It has different plates, and the composite tape springs are of 1 meter long each. We are using 4 of them, and they are connected using different plates. But why do we want to do this? We want to validate the design to be sure that it can deploy things in space, but also we want to check which sensors can be deployed with this. So we are having a camera and 2 inertial measurement units, one located the camera and IMU in the mid plate, and the other one in the tip plate, to record the deployment and also take measurements of the accelerations, and linear and angular, to be able to quantify which kind of sensors can be used for which accuracy. For example, if we hope magnetometers can be used, for which we've taken into account the distance between them and the magnetic fields. And after, when we analyze the data, we will do the benchmarking for this sensors utilization. So for explaining a bit more how our timeline is working, we launch from a rocket, as I said before, so we take that as the reference time, and we wait for the rocket to burn out. And as you know, the rocket, when it's launched, it starts spinning, so we have to deploy this mechanism, so we have to wait until it spins. And in the previous image, I showed that it's kind of large. It's 2 meters long, our whole mechanism. So the rocket diameter is only 356 millimeters, which is lower, so we have to eject our system to deploy it outside of the rocket. And to do that, we are putting a hatch. We will eject the hatch after the spin of the rocket, and this is how it looks like. The blue part is the skin of the rocket, in which we are putting inside our experiment, and there's the hole for the hatch. Apart from that, we are also using a camera to record the deployment. We want it for outreach, but also to make sure that everything's working while we are doing the experiment. And the hatch ejection mechanism looks like this. And this is the mechanism we use. You can see that there's a steel cable around it. This steel cable is the thing that retains the hatch. And it's cut with 2 pyrocutters, one on each side. So once we cut this retention mechanism, the hatch is ejected, because as you will see right there, there are 4 springs that are compressed, and then they are not, so they eject it. And that's how it looks like. But after ejecting the hatch, we have to eject our experiment, which we call FFU, which means free falling unit. And for that, we also have this mechanism that is inside the previous one, in which we include 8 ejection rails to make sure that it's ejected in the direction we want. We also cut it with a pyrocutter that is in the back in this case, and push the FFU once the mechanism is cut and it's ejected with a pusher plate. And here I put a video of how it would look like for the ejection from a previous team. This is recorded from the rocket, which is a bit turning, but this pan already. And there's the hatch and the FFU, which is black. So that's what we are aiming to do before performing our experiment. But you've seen that it's still turning once ejected, so we have to stabilize it for performing our experiment, and Julian will explain you how we want to do it.
Okay, so to make sure the FFU is not spinning anymore. We need an ADCS. So our ADCS will be composed of sensors and actuators, and with a software, we'll just receive some data from the sensors and use direction wheels to stabilize the FFU. So this is a view of the FFU. As you can see, it's quite small. It's 100 millimeters on both sides and 172 millimeters height. So it's 1.5 CubeSat unit. And now we can have a look inside of it to see what is it inside. So it's mainly 5 different parts. On the top, we have a recovery unit. Then in the middle, we have the reaction wheels, a battery holder, 2 cameras to record the deployment of the boom, and of course the boom itself. So everything here you can see is made by us in our own workshop with CNC or milling for the PCBs. So except the skin from the rocket, we are doing everything on our own. So it's quite challenging, but it's a good way to learn. That's nice. So you can see the reaction wheels are the main part for the ADCS. And then the recovery unit is a unit in which all the data of the sensors and the camera footage will be stored for analyzing everything when we recover this unit. And in this unit, you will have also the parachutes. So then, after the despinning, when we have the sun in the back, because we want to record the deployment of the boom, we are just before the apogee, because we want to have the most time in weightlessness possible for our experiment. And so we deploy the boom. And so the boom deployed looks like this on your right, and on the left it's when it's coiled. So you can see the change of sizes is quite important. As Sarah said, it's for implemented a lot of sensors, and for example we can put some magnetometers in it. So this change of length is quite challenging because we need to fit everything in a very small box, and then when it's deployed we need to have a connection between all the parts. So for this we have electrical harnesses between the different plates to provide power from the FFU to the camera and to the sensors, and we can also save all the data from all the parts to the recovery unit in which the boom is still attached. So yes, this is the boom deployment itself. So then when the boom is deployed, we will reach the apogee, and when we will go down, the parachute will be deployed at 5 kilometers altitude thanks to pressure sensors, and we hope to recover the recovery unit after a soft landing in the snow, because it will be launched in Kiruna in March, so it will be full of snow, of course. And once we have the data, the most important part is to do something with it to make sure the experiment went well. So for this, our main objective is to make sure the deployment was correct. So we will analyze the footages from the 3 cameras, and thanks to the 3 different points of view, we can recreate the whole dynamic of the deployment. Then also, the second step will be to look at the data from accelerometers and compare it to the different data from the sensors, either in the boom and also in the FFU, synchronize everything, and look if we can rely on the different data we have from each of the sensors. And after this, we want to use all of this to recreate the motion of the deployment, the motion during the deployment, and also we want to study the behavior of the boom, the way it will oscillate, and all this kind of movement to maybe because maybe later we want to use the ADCS to compensate the behavior of the boom and the oscillations. So yes, that's all we want to do with the data. It's quite challenging also, but it's really nice.
Yeah, this is our experiment, and just to finish, I wanted to share some insight that we've got through the development of this project. As I've said, it's quite an international team, so we've learned how to work, having been used to work from different ways, and how to work different people together, even though we have different ways to doing it, and to share different backgrounds. And I want to cite one of the previous team leaders of KTH that told me that Rexus Vexus is a microcosm of the European space sector, and it's the perfect place for study for students to learn how it works before getting to it really when we start becoming professionals. So thank you for your time. If you liked our project, feel free to check our social media. And yeah, thank you.
Thank you very much. We have time for questions. Mr. up there.
So we are actually working with a magnetometer which would be the boom. The question is how you can, how much stability can you guarantee for a 100-gram sensor on top of that boom?
That's what we want to measure. But this is a reflight experiment from a previous one that was performed with magnetometers. And those magnetometers were heavier than 100 grams. So the thing is the experiment didn't work well because the boom wasn't able to deploy. But from the tests that were done on ground, it provided the stability that was set as a requirement.
What about the cables?
Yes, the cables are done using an electrical harness that is able to fold properly around some spools. And the thing is, we are mostly only sending the data and the power. So with this electrical harness, it allows us. We're having some problems for the video of the camera, but we found a solution with a flex cable that can be implemented in the electrical harness. Thank you.
So you demonstrated the antenna and how it opens with a lot of force.
Yes.
How do you make sure that it does not open when it shouldn't?
For that, we also have the ejection mechanism we have for that also includes a cable. In this case, it's a fishing line that is coiled around. So we will cut it with a thermal cutter. Once we make sure that we've been ejected, we are outside of the rocket to ensure there are no problems with the rest of the rocket, and it's stabilized. And then we'll activate the thermal sensor and cut the fishing line. And we'll perform several tests after vibrations to make sure that it's not activated before issue.
And does this alter the rotation of the satellite when it opens?
Expectedly not. Like we want to compensate it with the ADCS, so that's why we are also doing the algorithm, but we are in the development process for that.
Thank you.
Thank you.
Thank you very much again. Our next presenter will be Laura Bettiol from FOTEC Forschungs- und Technologietransfer GmbH, and she's going to present about FOTEC's testing and qualification capabilities for small satellites. I give you the floor.
Thank you. Good evening, everyone. So yes, I'm Laura Bettiol. I come from your neighbor country, Austria. And I will talk about what we can do at FOTEC regarding testing for small satellites, and also what we do regarding propulsion systems. Yep. So we are located in Wiener Neustadt. It's a small town located about 40 kilometers from Vienna. We are a small company, a small research center, basically owned by the University of Applied Sciences. We have about 40 employees divided in 4 departments. I work in the aerospace engineering department, and that's what I will be talking about today. And then we also have aerospace engineering, engineering technologies focusing on 3D printing mostly, and innovative software systems, business engineering, and we participate in several different projects from national and with national and international fundings, for example, from ESA. Yeah, as I said, I work in the aerospace engineering department, and we have 3 different main focuses. So electric propulsion, chemical propulsion, and environmental compatibility testing. Let's start with electric propulsion. Particularly, we focus on FIP thrusters. These are field emission electric propulsion technology. Here on the side, I think this is the right one. Yeah. Here on the side, you can see our heritage propulsion system. It's called IFM Nano Thruster. And this one, the development of the FIP thrusters has been supported by ESA for many years. It was in orbit demonstrated in 2018, and at the moment there are about 200 units in orbit. The thrust range is about from 1 micronewton to about 1 millinewton. And at FOTEC, we not only develop our thruster systems, but we also want to test them. So we have the possibility and the equipment to do direct thrust measurements. That means we have thrust balances, and we have also plasma diagnostic systems, because this is an electric thruster, this is emitting ions, and we want to analyze the beam features of these systems. So here, for example, you can see an example of thrust balance. Here we are already at our 7th generation, so we have quite some experience with it. As I said, it's used for measuring the thrust or the force generated by our thrusters. And it can measure up to 1 Newton, so different ranges. It's using very precise electromagnetic force actuators, which have a provide very high stability and very low noise and very fast response times. At the moment, or since many years, we already sell this kind of technology to different institutions and companies in Europe and also in the Middle East. And we also provide these tests as a test service. The next device that we developed and that we also provide to the industry or to academia as a service and also as a product is RPA. This is used to measure the energy distribution of charged particles. In our case, we want to measure the ion beam properties, so we measure the energy spread of ions. And yeah, basically this one can be very interesting when we have a very wide energy distribution or energy spread, for example, in Hall thrusters. This is another technology that we are developing, or another device. Here it's a Faraday cup. It's commonly used to measure ion current. In our case, you can see it here. We have 23. They are mounted on a boom that is rotating around the thruster to create the ion current distribution and measuring the divergence of the beam and also the thrust misalignment or the offset of the thrust vector. In our case, it's we have 0.1 degrees resolution on the horizontal and up to 4 degrees on the vertical, which is sufficient for us and for our measurements. And yeah, it's very precise, having 5 picoamps peak-to-peak noise, which is very good. And this is thanks to the fact that we have the electronics directly embedded into the Faraday cup. Therefore, we don't have very long cables where we lose. Yeah, we get higher noise. Yeah. Then we go to chemical propulsion. Here you can see we have our monopropellant thruster system. In the different pictures, it's planned to go between 0.25 to provide up to 1 Newton of thrust, and we also develop bipropellant thrusters up to 10 Newtons of thrust. At FOTEC, we want to get away from hydrazine, which is not a very good propellant at the moment to use, and move towards green propellants. And what we also want to mention with our thruster systems, we use a lot of additive manufacturing systems and technologies, so that we can also use different materials, like in this case ultra high temperature materials, like some special alloys with iridium and rhenium. This is the vacuum chamber that we use for the tests. You can see it here, and here you can see the thruster. It can. This one, this chamber is designed to be used for thrusters developing or generating more up to 20 newtons. And it's possible to use it with a vacuum pump up to 20 kilovolts, creating a 1 millibar environment in vacuum. Of course, it has many different sensors, for example, pressure, temperature, and load cells to measure the thrust vector. And last but not least, we also have some equipment for doing environmental compatibility tests. We have the possibility of doing some vibration and shock tests in our facilities. And also we develop radiation-tolerant electronics based on COTS. And we also develop sensorics and test facilities for SCE tests. We also do tests for third party in another facility nearby for what concerns also radiation, single event effects tests, and EMC. More in detail, we have a shaker and a sleep table, and what's special about it is that we can reach a sinusoidal force up to about 9 kilonewton, and and with a payload up to 5 kilos. So far we have tested our thruster systems, and it can be used, for example, for CubeSats. Recently we tested a CubeSat from University of Vienna, for example. Then we can, we have the shock test available. It's possible to measure in all 3 axes with different hammer masses, drop heights, and materials and target materials. That means we can adapt the energy of the impact. In this case, the payload can be up to 3 kilos. And and also here we have used it for testing thruster systems and small CubeSats. Last but not least, we have a quite large thermal vacuum chamber. So here, basically we have a thermal shroud that is shown with a very nice golden foil. It's basically 2 times half a meter square, cube. And it's possible to reach between minus 150 to 150 degrees with liquid nitrogen for the cooling, of course, and with electric heaters for heating up. So as a conclusion, I want to just give an overview of what we do at FOTEC with basically presenting our propulsion systems and what we do regarding testing for propulsion systems and also for component systems and CubeSats up to 3U. The most recent additions were the big vacuum chamber. We have two with 14 cubic meters size. The thermal shroud was developed last year. And we also have the possibility of integrating and assembling everything in a clean room. Thank you. Thank you for your attention.
Thank you very much. We have time for a question. Yes, Mr.
Yes. So the cubes, propulsion system. I don't know if I can go back. Oh yeah, this is the one. The propulsion system is basically the size of 1U, 10 by 10 by 0.9 more or less, and it fits in 1U. For example, you can see here. This is let's say a design for the CubeSat climb from University of Applied Sciences that will be launched probably next year. And you see in the back. There's one of our thrusters. So yes, the answer is yes.
Thank you again. Our next presentation will be held by Zoltán Tóth from HIN Research, Development and Innovation Ltd. And the title of his presentation is Thermal Performance Characterization of Battery Insulation on ATL-1 picosatellite mission. I give you the floor.
Thank you very much. And good afternoon for everyone. Or good evening for someone, if you think. My presentation is with the study of thermal performance characterization for battery insulation on a satellite mission. And it was a teamwork of diverse experts. And you see the name of our satellite, ATL-1. And my words about ATL-1 will not be the first today, because our colleague Caius Reza mentioned this in his keynote lecture, but I will talk about it from another different point of view, or special experiment. Sorry. So I have to start with a short apology because I'm not enough familiar in material sciences, because our colleagues are who are the specialists of material science and engineering physics. I'm astronomer and expert of electromagnetic radiation and solar radiation measurements, but I'm a specialist of data processing and data analysis and data interpretation. So that is the reason that I am the main author, because I've made the whole process and analysis of the data set of our experiment. Okay. So a short outline what I will speak about. First about ATL. satellite and its orbital data. After it, the experimental setup and some words about data availability. After it, I speak some words about evaluation method. After it, a discussion about the results. So it was a collaborative experiment of two private companies. One is our company, the H-ION, and two universities, Ötvös Lóránt University, the Department of Chemistry, and from the Budapest University of Technology, two colleagues, two electrical engineer colleagues designed and made the electronics and the telecommunication of the ATL-1. The launch was, oh sorry, you know, our satellite moved backwards in time. So sorry, it is, naturally it is 2019, so it was a mistake. So three main aims were on this mission, on this about 10-month mission. First is our experiment. We have special in-house developed thermal insulation materials, and we studied their thermal insulation capability, that we insulate with them batteries on board. Now we speak about the results of this. Another aim was, it's a bit difficult for me. Aim was the testing of the energy supply system and the data transfer and data receiving system, and the third was special measurements, electropollution, cosmic rays, and so on, but they are not topic of my presentation. You see the coordinate system. Sorry, they are too dear to each other. The coordinate system of ATL-1, and it is a drawings from ATL-1. They are the letters with which we name the sites. So they were the sites that we use for mark the parts of the experiment. Okay, some data from the orbit. You can see the orbital period, inclination, mean altitude, perigee, apogee, daytime and nighttime. That is not the terrestrial daytime and nighttime, but special for the satellite. And on this figure, you can see the mean altitude, perigee, and apogee. They have some bimodal period, and this where it burn out in the atmosphere. On this figure, you can see the daytime duration of daytime and nighttime at the orbital period of the satellite. Okay, data availability and data used. It is only 4 lines on this slide, but to work on it was about one or 2 months for me. So you know, in this experiment was a pilot experiment. Nobody, as far as we know, nobody made a successful experiment like this so far, or at least hasn't published. So, and in an experiment like this, many difficulties arise in data transfer and some missing data. We have some longer periods with missing data and data with very high uncertainty. So the data reliability was very variable, and it was very important for us for the processing to get data set of very high reliability for the studies. So I've made a special data quality study based on which we select a period, a series of days that had suitable reliability, and it was this period. So the results that I will speak about concern this period. Okay, experimental setup. You see the type of the battery, 4 batteries, this type of batteries we used. Each in case the custom-made copper housing. These are the dimensions. And my colleague made some modifications. For example, new electrodes, own developed electrodes were used in the battery. Space between each battery and the copper houses was filled with the special insulating materials, and they are the special materials developed by our company. The first three material, and the fourth is the Kapton tape or Kapton foil. It is a custom-made, well-known and relatively frequently used insulating material, and these are the names that we used for it, and I also used these names in the next slide that you will see it: porous fiber, cryogenic powder, composite, and the Kapton itself. Okay, this is the battery, 3 battery with sensors, and final construction of the battery pack, and it is the drawings from the battery. Four thermal resistor were affixed to the batteries, and a fifth resistor, PT100, the well-known PT100 thermal resistor, and these are the places of the 4 resistors, and the fifth was affixed to the other side. So not the battery side, but the other side of the board, of the battery board. And the first four points, they were insulated, and this fifth was the reference because it gave uninsulated temperature. Okay, I speak about evaluation methods. We made 3 types of studies to recognize the best insulator material among the 3, because there was no possibility. There was no possibility to measure quantitatively the thermal conductivity factor on board on the satellite. We have to find out a practical parameter, a quantity for this, and it was the thermal insulating intensity. That was the difference of the maximum temperature from Kapton and the minimum temperature of Kapton and the maximum temperature of the given certain material M and the minimum for it. Maybe at first you are surprised that the reference is on the numerator and not in the denominator, but the reason is that we expected that the thermal insulation intensity would be better for all materials than for the reference materials, and we expect more than 1 or more than 100% for our materials. That is the reason that we used it, and the normalized factor is on the numerator. Okay, I'll try to hurry. We studied the cyclicity of the temperature because the temperature make very regular cycling as a result of the periodic orbit around the Earth, and we study the cycle amplitude. The third is the effect of start and termination of the solar irradiation on the measured temperature during the orbiting. You know, when the satellite emerge from the Earth's shadow to the radiated area, and after it re-enter the Earth's shadow, there is a momentary change in the irradiation that is the main source for the heat for the satellite, and that time the temperature change the sign, and we studied the duration. We called it response time. When the temperature for the different materials start to change after the time of this transition. We know it on sun, off sun, and off sun, on sun transition. Results. Sorry, I try to speak. I'm too long. Okay, thermal insulation is intensity for the four sides. It shows that the porous fiber performed the best. There was some contradiction for the composite, but maybe it was the problem of the layer formation, and maybe the structure changed during the ascent when the ATL-1 moved to its orbit. It is the cyclicity of the temperatures for the several sites, and it is a reference, and it shows that our materials perform considerably better and has effective insulation capability because the amplitude higher for the reference site that is uninsulated. Also, these results confirm it. This is the daily cycle amplitude for the studied period on side X for a selected side, arbitrarily selected side, and it means that porous fiber that has the best thermal insulating intensity, if you from the previous slide, and you will see that the porous fiber has the lowest amplitude. It means that it has the best thermal insulating property. This lower figure also confirms this for the several sites. This is a summarized table for it, and also it confirms that porous fiber is the best. If you see, M's are the mean of daily average cycle amplitudes for the whole period, for the whole studied period, and the STD is the standard deviation, and you will see that the lowest cycle amplitudes are considerably lower for porous fiber than the other. So it means also that the porous fiber was the best, performed the best. Okay, and it is one of my last slides. It is the off-sun, on-sun transition. You see that the response times, these are the response times in minutes for the four materials. Also it confirms that porous fiber the best because it had the longest response times. The reference was very short. It means that all of the insulator materials were effective insulators, and you can see on this figure the on-sun off-sun response time on a selected side for 1 day. Also, you see that porous fiber had the longest response time, and also this is response times for the different sides, and it means that the reference had the shortest response time, so the insulators operated well. Considerably more information will be in our proceedings paper, naturally, about this. And this is my last results for on-sun off-sun transition when the solar irradiation disappeared. And you see that it is very interesting because the response times are considerably shorter than for the off-sun on-sun. If you remember, they were 12, 13, 14, up to 17 minutes. And in this case, when the solar irradiation disappeared, it was 2, 4, or 5. So it means that the insulation effectiveness is far more sensitive to irradiation change from finite value to 0 and in turn. We didn't find a reason for it so far. It is one last example for the red line shows the disappearing of the solar irradiation, and these curves show the temperature variation after it. You see that for the reference in this case, the temperature decreasing immediately starts when the solar radiation disappeared. Okay, I seek the summary, and thank you very much for your attention, and sorry for I was too late.
Thank you very much. As the time has been used, those questions which are in you, feel free to ask directly from Zoltán, but this time we skipped the question session and invite the next presenter. András Pál from Konkoly Observatory will present us about fast and flexible developments of digital logics applications in the first Hungarian astrophysical satellite, the GRB Alpha.
Okay, thank you very much. First, I will start to learn how this thing is working. Okay, not that bad. Okay, so in the next 10 plus minutes, I'm just trying to summarize what is GRB Alpha in principle and what did we do, what can be useful for other projects in the future. Okay, so this is somehow the table of contents. First, let's talk a little bit about the heritage and the backstory and whatsoever about GRB Alpha, which is Hungary's first astrophysical satellite mission. And also, this is now, to date, at least, the smallest astrophysical space observatory in the world. So you know that James Webb Space Telescope is the largest one, so this is the smallest one. So I will talk a little bit about that, how these small satellites can contribute to astrophysics. And in particular, the second half of this small presentation, I will talk a little bit about those parts of the mission which is up there, but still can be used for further development, adjustments, improvements whatsoever. And also talk a little bit about what is the lessons learned part of the mission, which can be useful. It can be any kind of useful stuff for other missions and projects and so. So gamma ray bursts, short GRB, were discovered in the late 60s by accident by this constellation of satellites devoted to detect nuclear explosions. So it has a little bit military backstory. And because of that, the scientific part that, okay, these astrophysical events really are astrophysical events and have some sort of cosmic origin were backlogged by 3 or 4 or something like years, so it's quite long because it was, classified. And later on, it turned out that the spatial distribution of these events are quite homogeneous, so they are either from nearby, so very nearby, or from cosmic scales, because otherwise you would see the ecliptic plane or galactic plane or some intermediate scale structure of the universe. And these events are detected in the gamma spectrum and last for a couple of seconds, couple of minutes, so quite short events, and there are no similar events. Yeah, okay. And there are two theories merging of massive compact objects like neutron stars and black holes, or the explosions of quite massive stars called hypernova and things like that. And we were just thinking about that, okay, this is fine, but how can small satellites, small means CubeSats, 1, 2 unit CubeSats, contribute to this type of science? And we started to draw this type of images, which is not on scale on any part, which means that it's good for proposals and reports and stuff like that. But anyway, this is the concept that, okay, here is a GRB somewhere nearby or not that nearby, and a swarm of satellites will detect it sooner or later, and using timing analysis, we can figure out that gamma radiation is originated from where, because gamma radiation is very hard to focus. So we started to build, after getting some sort of funding, this detector system, which is called GRB Alpha. This is the detector. It fits in a 1 unit CubeSat, so the detector itself, the core part of the detector, has a size of 7 by 7 by half centimeter, so it's small. It has some fancy photon counter electronics, and all put in collaboration with Czech and Slovakian and Japanese colleagues in a form of a CubeSat. So besides, getting the money and spending the money, we were also contributing with those teams and companies. So we had finished the satellite at the top of COVID. And this is the main part of the detector of the satellite in terms of the scientific payload. So analog and digital electronics, somewhere over there, and the scintillator detector is somewhere over there. So, yeah. And we can say that this is the smallest astrophysical observatory to date, and it is in orbit since more than 1130 days, so it's still operational. I was communicating with the satellite this morning, so it's all fine. Of course, the mission operation doesn't look like this. That would be great, but it's just a small screen with just a couple of windows opened, and of course, with some improvements, we can control it from a tablet or smartphone, so it's quite fine. And of course, radio communication is not that fancy. That would be great, but instead of that, we have some radio amateur stations, which is used for controlling the satellite. This is the station registered to me in practice, and there are also stations which are responsible for downloading the data. So these stations are, on the other hand, these are, it's a quite, I would say, funny thing that it's simplex stations and not half-duplex stations, which is not that common, I think. Okay, and of course, scientific results are something which are expected from a scientific mission. So when the satellite is orbiting the Earth in a polar orbit, polar or sun-synchronous orbit, because that was the cheapest, it means that it goes into the noisy regions, like polar bears or South Atlantic anomaly, but otherwise the signal can be there, so at the background you can detect something, and otherwise these maps also look cool, but it doesn't relate to the GRB science, but it's much more nicer. But of course, GRB light curves are also nice, so these were the first 3 detections. You can figure out that from the dates, it's late or September 2021. And this event was also detected by our mission, and this is for this famous GRB, which is the most powerful or energetic GRB detected in human history, but probably it's not related, it was not as big, luckily, as one of the mass extinction events happened 400 and something million years ago. So we were quite lucky with that. Anyway, so next part, I would just like to summarize a little bit that why this type of mission is useful besides, oh, sorry, how can I go back? Besides, helping astronomers to search for the secrets of the universe and doing radio amateur activities at the same time. So I would like to talk a little bit about those parts of the mission that you can still do development and continuous updates to date. So these are related to software and some components of the hardware if the hardware is implemented in the form of programmable logic. So One reason that why we started this is not just because we are lazy, but the deadlines are close, so it's easier to write something which is capable to upgrade itself, okay, more or less safely. And then we can work in a little bit more peaceful way when we are waiting for launch. So that's better. And of course, it happened this way. And after launch, we were able to do quite significant upgrades on the system software design and in some components of the data acquisition hardware at the same time. And of course, the limitations are just the imagination and of course the resources in the FPGAs and the MCUs. Okay, so instead of just making a kind of blob of wires within the programmable logic, a kind of development started which is based on a soft system on a chip design. And this is because the learning curve of FPGAs and programmable logic looks something like this. Yes, so it is not that easy to learn, but if you can separate the functionalities to resemble to normal MCU or computer or desktop programming, then it really helps a lot. So that's why in this system there is a CPU that you can program in C, C++ in your favorite programming language, which can be compiled, uploaded. You have normal peripherals that is well known from the industry, and all of the rest, which is the scientific payload, which are the hard real-time part of the detector systems, are implemented as a special set of peripherals within the FPGA. So Verilog or VHDL is needed just for this type of things. So these are the soft parts, basically, these two little thingy here. And of course, because of the redundancy and increasing the sensitivity, we have doubled, so these two are also that. And of course, it works as a kind of cafe-compatible tabletop electronics, so we can play around it anytime, anywhere. Just a single USB cable can simulate all of the rest of the mission, which is good. And this is a kind of system design that is implemented there. This is working now at the present moment, which looks something similar, and the scientific stuff, which does the interesting thing, you know, this discovery of GRBs and things like that. This is this very simple and stupid thing here. And otherwise, with upgrades, we can make it more complex, more complicated, using more complicated CPU, system design, whatsoever. So this is just a quick summary about this system design and why it is interesting, because there are future applications like imaging detectors, other type of astronomical application, type critical platform components, and of course we would like to incorporate this design in SDRs, and we would like to be a little bit more ESA compatible at the same time. So this is just a quick set of images starting from modules used mostly in education and development, up to prototype of imaging detectors for satellite missions with a size of 100 plus kilograms. So it can be incorporated in many types of missions sooner or later. So thank you very much.
Thank you very much. We have time for question.
Yes, please. Would you try to make this whole setup with picosatellite? So not with two satellites or on smaller size?
Well, good question. Not yet, but it is on the short list. Yes.
Other question?
So, with FPGAs, there's a possibility of partial dynamic reconfiguration, so you can change out part of the design. But how can you do it such that the SoC is programming the same regions that it's sitting on?
You mean self-programming feature for the CPU or self-programming feature for the FPGA? Because these are two different things. So boot ROM support and self-upgrade of the software running by the soft core within the FPGA is possible. But of course, it is also possible to reprogram by own by itself the FPGA bit stream using the same peripheral set, but it's not safe. So the first one is safe, the second one is not safe. So that's the difference.
Well, I was talking about how you switched from the AVR 2.5 core to the RISC-V
Yes.
core.
Yeah, you can do it. I mean, there is no objection against. It's not that, okay, you switch from an 8-bit to 32-bit, you would say that, okay, it's much more complicated, but it's not true. RISC-V is a very well-designed thing. AVR is not that well-designed. So you can really see the difference when you start to work with stuff like this. So you can do it, of course. Of course, it is unable to reprogram itself unless you do a full reload or update of the configuration chip using the FPGA logic itself. You can do it. So in that sense, the AVR can upgrade itself to be a RISC-V, okay, but this is not the goal.
I see. So you downloaded another core that then programmed the AVR core. Or
there are many options. So there is not just a single option for upgrade. So there are many kind of interconnections and glue logic and stuff like that between the MCU and the FPGA and the configuration chip at the same time. So, okay.
Thank you very much. Our last presenter, Máté Galambos, a local guy. He's from Budapest University of Technology and Economics, and he's presenting us under the title Testing Remote Clock Synchronization with GPSDO-s and a Free Space Laser Communication System. I give you the floor.
Thank you very much. So, good afternoon, everyone. I hope there's still some people who are awake and have the energy to pay attention to the presentation. What I'm going to be talking about is how we can synchronize clocks remotely, and in the previous presentation we heard a little bit about this, why this might be useful, that if we have very precisely synchronized clocks, we might be able to tell where gamma burst is coming from. Now, why we want to do this is quantum communication, specifically free space quantum communication, but it's just a different application. The goal is basically fairly similar. That we want to have two of these time tagging devices. Let me see if I can. Okay. So two of these time tagging devices that are synchronized to one another, and we also have some reference master clock, one over here and one over here, that basically give an oscillator, a very precise oscillator, synchronized to global positioning systems. So essentially atomic clocks placed on satellites. Now, if we want to synchronize two of these clocks, then we have two possibilities. One is just to rely on two of these GPS disciplined oscillators, these GPS clocks, and synchronize them that way. The problem is the signal takes a slightly different path, and there are reflections, and of course the clocks themselves don't always synchronize perfectly. So this can be a bit of a problem. And the other possibility is that we basically just use one GPS oscillator, which is right here, and use some kind of channel, like a free space laser channel, to transmit this clock information to the other side. This way the two sides are very well synchronized with each other, not necessarily with the rest of the world, but for us that is perfectly fine. Okay. Also, we wanted to test our devices, so we have some devices that are built in-house, such as the clock transmission system and the GPSDO-s, and also we have some other devices like the time tagging devices that are commercial, and we also want to characterize them as well. So, let's start with the GPSDO-s, which we tested in the lab, and what we found is that Basically, we have connected two of these GPSDOs to the same time tagger, and we use the time tagger to create one of these start-stop histograms, which works the following way. So one of the signal basically starts a little stopwatch, the other one stops it, and we count how many times we see a certain delay between the two signals. The more narrow this histogram, the better the synchronization between the two. And we perform this test for various data collection times from 0.1 second to 30 seconds. And we see a certain increase in this uncertainty, this standard deviation of the data. Basically, for 1 second or less, this is mostly 60-70 picosecond that we see. This is the jitter. And as we go for larger data collection times, we can see about 1 nanosecond to a few nanoseconds jitter between the two. Okay, now this is the lab, and let's see what happens if we go outside. And some of you may recognize this neighboring building where we done our test, where we could go for 85 meters from one GPSDO to another. And basically, we place them a little bit farther away, still connected them with a long cable that we have characterized previously, and we have known that it doesn't disturb us too much. And what we have seen is basically that this jitter was still behaving very similarly, although the standard deviation has basically doubled. Okay, so that is all fine and good, but how does this relate to our laser clock transmission system? And first we tested it in the lab, and what we found was that basically, first of all, what did we do? So we have connected this GPSDO to a time tagger directly and to the clock transmission system from which we connected it back to the same time tagger. And what we found was that for 1 second data collection time, the average standard deviation was still around 60-70 picosecond, let's say 66.18 picoseconds. And the really interesting thing that we found, which is comparable to what we would see from two GPSDOs, that this does not depend on the measurement time. So even for longer measurement, we get the same result, which is perfectly fine, because this is exactly what we see if we connect this GPSDO through a delay line back to the same time tagger. So this is a very nice result. But what happens when we go outside? Because there are, of course, these optical turbulences that you can see here that can interfere with our signal. And the answer is, if the alignment is good enough between the transmitter and receiver, and of course the weather has to be cooperating with us as well, then we can have a very, very good alignment between the two. Again, the standard deviation doubles compared to the lab, similarly to two GPSDOs. However, the standard deviation doesn't depend much. It starts to depend a little bit on the data collection time, but doesn't depend much on it. So for longer data collection times, using this laser clock transmission system is actually much better. And here you can also see the histograms for various data collection times when we have good alignment. However, when we don't have good alignment, and admittedly this data is for the good alignment, when we don't have good alignment, every once in a blue moon you see these weird shapes that show up and make the jitter worse. And the longer the data collection time, the more likely that you are going to run into one of these weird events. Okay, so then we went a little bit further, and we wanted to test this system between our building that we are in right now and the neighboring building. So what we have done was we placed two of these the transmitter and the receiver next to each other on a rooftop, and we've placed a mirror on the other building that we could move, and we could increase the distance to twice 30 meters, so 30 meters from the transmitter to the mirror and 30 meters back to the receiver, to 2 times 100 meters. And unfortunately, we could only achieve a good alignment over 30 meters, and the rest of the time it wasn't that good, mostly because of the mirror, actually. So the mirror itself was a problematic part of this system, as it turns out. However, when we have good alignment, we have about half a nanosecond jitter over a 5-second data collection time, so it is still quite good. But then we started to wonder, okay, what happens if we have a shorter data collection time? So how do these complicated shapes emerge? And this is what the next slide is basically about. We have analyzed the data retroactively and created this simulation, this animation, where each of these frames of the animation in the lower part basically represent 1/100th of a second of data collection. And on the top half, basically, you see the cumulated shape as we gather more and more data. And as you can see, most of the time we have a very, very narrow peak that just wanders around, and every now and again we actually lose contact between the transmitter and the receiver completely, and you have this flattened shape down here in the short-term measurement. Okay. But we wanted to test our system as far as we could take it. So we performed the test over half a kilometer and see what happens without a mirror. And one of actually the transmitter was here at this building, and the receiver was at a nearby dormitory on top of Schönherz dormitory on the rooftop. And as you can see, there is quite a bit of turbulence over this distance, so the air introduces a bunch of problems. However, if you have good alignment, it is actually quite good. So the standard deviation goes from 1 nanosecond to a couple of nanoseconds. So, but admittedly, this is still for a good alignment. When you don't have this good alignment, you don't get data this good. And also you have to take into account that you have 2 GPSDO-s, so basically you have to take into account that the jitter of that adds to the jitter of the clock transmission system as well. Okay, and we wanted to see how far we can take this, and we wanted to see what the limit of our system would be. So we performed a test over 3 kilometers between the Schönherz dormitory and the Budapest 1 building, where the headquarters of Vodafone is. And unfortunately, this didn't work as well. But this, 3 kilometers was pushing it. The system was not designed for this distance, and what you get is basically usually nothing. But every once in a blue moon, you get a little bit of a flicker of a signal, as you can see here. Just every once in a while, you get a little bit of a flicker, and you get a little peak like this. And basically, I just want to say a huge thank you to all our hardworking colleagues and students, without whom this would never have been possible. And with that, I thank you for your attention.
Thank you very much. We have time for questions.
Yeah, absolutely. I think this is absolutely possible. Again, I think optical communication between satellites is a fairly new field, so it is still, I think there are a huge number of open questions, but I think it's definitely the future of intersatellite communication, and I think there is quite a few possibilities there as well.
Thank you. Further questions? Well, then, thank you very much for your nice presentation. And as a summary of this session, well, when I was reading the title of the presentation, it was quite suspicious that we will have a very interesting and diverse topics from all the presenters, and it turned out that they have not only been diverse, but also they have been interesting. So let me thank for the presenters for their nice presentations, also for keeping the time frames, more or less. Otherwise, also let me thank for the audience for their everlasting interest in the presentations and motivation for being informed or on the status of research, on the status of space activity in general. So I would like to close this session, and as a final act, I would like to ask László Bacsárdi to wrap up the whole day.
Thank you so much, Lóránt, and thanks again for chairing this afternoon session. I was really happy to see the variety of abstracts that we have received during the abstract submissions, and I was really happy to see the poster presentation in this afternoon, as well as to listen to different interesting technical talks in this first section of science and technology. And right now I would like to invite everyone to join our second day tomorrow morning. And I remember that in 4 years ago we organized the Space Conference at the very end of February, just 1 week before the lockdown started here in Hungary and all over Europe. So at that time we were really lucky because our space conference was one of the last space conferences, not only in Hungary but in the region for a quite long time. And 2 years ago, when we came together again, we decided to organize a hybrid conference. So 2 years ago, the first day was live streamed, similar like we did it this year, and the second day was an online day. And when we were thinking how we will do with this year edition, we decided to follow the same pattern. So today was a really good opportunity to meet everyone in person and to have fruitful discussions during the coffee breaks and before the official start of the conference as well. But tomorrow we will have the opportunity to listen to presentations of people who were not able to travel here in person. So there will be Hungarian presenters as well, but there will be many international presentations. So I invite everyone to check the emails with the Microsoft Teams link, which have been sent out this morning for the registered participants as well a few days ago. We will start at 9 in the morning with an invited talk about the JUICE mission, the Hungarian contribution to the JUICE mission. After that we will have several interesting talks regarding science and technology. Then we will have the highlight talk from USPA. We will have a lunch break after that, and then we will start our section on education and outreach, starting with a highlight talk as well. And we plan to finish the conference tomorrow around 3 p.m. local time here in Hungary. And with that, I hope that you enjoyed the first day, and see you tomorrow. Thank you very much for your attendance.